Hello everyone, our next problem is absorption in packed tower. Let me read the problem statement. A reactor effluent contains 2 mol percent ethylene oxide, EO, in an inert gas. It is to be scrubbed with water at 30 degrees Celsius and 20 atmospheric pressure. Gas feed rate is 2000 pound-moles per hour. Pure water enters the scrubber at 1700 pound-moles per hour. Cross-sectional area of the column is 10 feet squared, and Z, which is the height of the packing, is equal to 24 feet. And packing is made of 1.5 inches of pall rings. It looks something like this. And some conditions are given. Vapor-liquid equilibrium ratio, K, is given. It's 0.85. And small kya and small kxa's are given, which are the mass transfer coefficients in interface and bulk. And we need to find 4 things. A, big Kya. We need to find the mass transfer coefficient for bulk and equilibrium. B is height of mass transfer units. C, number of mass transfer units. And lastly, we need to find mole fraction of ethylene oxide in exiting gas. So the problem statement, when we draw it, it looks something like this. Water enters from the top, exits at the bottom with most of the ethylene oxide. Ethylene oxide in an inert gas enters from the bottom and exits from the top, and it still contains some amount of ethylene oxide, which we need to find. And height of the packing is actually equal to height of mass transfer units times number of mass transfer units. And we already know what is Z, therefore we can find HOG and NOG. So firstly, the problem statement asked us to find the big Kya. And in order to find that, we need to start from the beginning and understand what is the meaning of small k's and big k's. So first of all, we need to draw our bulk vapor and bulk liquid. So in this case, this is the gas containing ethylene oxide, and this is the water to scrub the ethylene oxide. So they are meeting, they are gonna be touching each other in order the mass transfer to go on, and using the packings 1.5 inches of pall rings. So let me start with the y and the x's. Y is somewhere here and x is somewhere here. Why did I draw the y on top and x in the bottom? Because the concentration gradient is going upwards here. So ethylene oxide mole fraction will be bigger than the x. X will be almost 0 because water does not contain any ethylene oxide. So ethylene oxide, the mole fraction of the vapor will go somewhere like this and go down like this, and x mole fraction will go somewhere like this and meet here. And this point is called y interface, and this point is called x interface. So basically they're meeting at the interface, and the mole on the mass transfer for the y to yi and x to xi is basically the mass transfer rate to the interface. And also there's a mass transfer rate between the bulk liquid and bulk vapor to the equilibrium. So in this sense, the equilibrium mass transfer is for the perfect scenario, because it is assuming that y is going to be perfectly going to be equal to x. So this is x star, and x will be equal to y. So it's assuming that the mass transfer will be perfect. So this will be X star. So this means that X is going to be equal to Y, and the transfer is going through 100%. And basically Y and X star is going to be in equilibrium with each other, and X and Y star will be in equilibrium with each other. And the fact that Y is going to the Y star, X is going to the Y star, and Y going to the X star is denoted in the mass transfer rate to equilibrium equation. So now we need to use a graph, Y and X graph, in order to understand the operating line and the equilibrium line using the X and Y's and Xi and Yi's. So operating line is here, and the equilibrium line is here. So our bulk liquid and bulk vapor mole fractions are denoted as X and Y. And in the equilibrium line, since X is going to be constant, and in order to denote the Y star, we need to go down, and the X will be constant and Y star will result in. And when we go to horizontally, we find X star and Y will not be changed. So these are the points that are used for the mass transfer rate between the equilibrium and the bulk. So what about the mass transfer rate between interface and the bulk? We draw it somewhere here. So this will be the interface point, Xi and Yi. And let me write the mass transfer rate between interface and bulk. Bulk meaning bulk vapor and bulk liquid. So our mass transfer rate is equal to small kya times y minus yi equals to small kxa times xi minus x. So this is the rate that is leaving the vapor. Rate of basically the ethylene oxide, and this is rate of ethylene oxide entering the liquid. So as you can see, we can also write it as this, y minus yi over x minus xi equals to minus kxa over kya. So this is a slope for denoting this slope. So this slope is equal to minus kxa over kya. And when you see y minus yi over x minus xi, then you can see basically this and this. So basically this over this is equal to this. So the kya is mass transfer coefficient for the vapor side, and kxa is also mass transfer coefficient. A is actually interfacial area. This is also the same. And these y minus yi and x minus xi These are actually called driving forces of mass transfer. These are the concentration differences. So basically, what is actually driving the mass transfer is the difference between concentrations. Because the concentrations are different, mass transfer is occurring. So now we know that mass transfer rate between interface and bulk, how it is written. Now we need to write mass transfer rate between the equilibrium and the bulk. And for that we need another graph. So on the equilibrium curve, equilibrium line, we can say, sometimes this equilibrium curve is not straight, but in this case it's straight. So it's easier for us to calculate because the differences between x and i's and x stars and x i's are not going to change. They're going to be constant. So this will be easier. We do not need to use integration. We can only use the differences in concentrations. So in order to write down the overall mass transfer rate, towards equilibrium, we need to use this graph. So R is equal to big KYA times Y minus Y star equals to big KXA X star minus X. So this bit is rate entering liquid, and this part is rate leaving liquid. So we know that this equals this, but we also know that small r is equal to KYA equals to Y minus YI equals to KXA times KXI minus X. So we are going to use this and use this in order to create something different. So we're going to use Y minus YI, X minus XI equals to minus KXA over small kya into this equation, and we get the following equations. Big 1 over big kya is equal to 1 over small kya plus 1 over small kxa times yi minus y star over xi minus x. And another equation for the big kxa, 1 over big kxa is equal to 1 over small kxa plus 1 over small kya times x star minus xi over y minus yi. So what is the point of doing this? The point is to relate the big kyas to small kyas and big kxas to small kxas. And these equations also can be further simplified. So when we see yi minus y star over xi minus x, on this graph we can see yi minus y star is here and xi minus x is here. So this is the slope of equilibrium curve, and slope of the equilibrium curve is actually equal to big K. So this will be simplified to big K. And the bottom bit, x star minus xi, is actually this bit, and y minus yi is actually this bit. So this over this is 1 over k. So this can be simplified to 1 over k. So now we can write the simplified version. 1 over big Kya equals to 1 over small kya plus big K time over small kxa. The second equation will be 1 over big Kxa is equal to 1 over small kxa plus 1 over k times small kya. So this actually is going to be used in our problem now. So we need to find big Kya. So in our problem statement, big K is given, small Kya and small Kxa are given. So we can plug it into this equation. 1 over big Kya is equal to 1 over small Kya is equal to 100 pound moles per hour per feet cubed, plus K is equal to 0.85 over small kxa, which is equal to 85 pound moles per hour per feet cubed. So big Kya now is equal to 50 pound moles per hour feet cubed. So for the finding of height of the mass transfer units, we need to know that Z is equal to HOG times NOG. And HOG is actually equal to gas feed rate over Kya, which is mass transfer coefficient overall for the equilibrium, and S is actually the cross-sectional area of the column. And NOG, we can later see that it is equal to the integration from the y in to the y out, and 1 over y minus y star. And why this is integration? Because sometimes equilibrium curves are curved this way or curved that way, so the concentrations of the y's are different. So to find the HOG, we need to plug in what we know. Gas feed rate is 2000 pound moles per hour, and Ky is 50 pound moles per hour feet cubed, and times the cross-sectional area of the column, which is 10 feet squared. And when you see simplify all the units, we get feet. So when you plug it in, 2000 over 500 will be 4 feet. So this is our height of the mass transfer units. So for C, it's quite easy. We already know that number of transfer units is equal to the integration of 1 over y minus y star. But why do we need to do that when we know that Z is equal to NOG and times HOG? So we know Z and HOG, so we just find the NOG by dividing Z with HOG. We know that from the problem statement it has given us that Z is equal to 24, and HOG we calculated earlier, it came out to be 4 feet, so 24 over 4 is equal to 6. And NOG doesn't have any units because it's how many transfer units there are. So there are 6 transfer units, and all the transfer units have 4 feet high. So now we need to find what is y out, and from NOG equation we know that the integration of the 1 over y minus y star is equal to NOG. So we're going to use this equation. But first we need to know what is y minus y star actually. So basically y is the initial ethylene oxide that we want to transfer it into the liquid. And y star is actually the amount that ethylene oxide was transferred. So the difference between y minus y and y star is actually y out, which is ethylene oxide, what is left in the gas. So in our case, our equilibrium curve over here is straight. This is our operating line. And since these are parallel to each other, not parallel specifically, I mean, basically lines, so y and y star, the differences will be the same. So we don't need to do any integration actually. We can just say, since y minus y star is equal to y out, we can just say y out NOG, and the top will be delta y. And delta y from the y in to y out will be y in minus y out over y out. And this will gonna equal to 6 because we found from the earlier calculation that NOG is equal to 6. And actually we know what y in is from our problem statement. It said a reactor effluent contains 2 mole percent ethylene oxide. So 2 mole percent is 0.02 minus y out equals to 6y out. So y out is equal to 0.02 over 7 equals to 0.00286. So this is our calculation for y out.